Well, it's a pleasure to have you all tonight for our debut of Frontiers Online with a complex topic, simulating the risks of solar weather. And we have a large team, so it's my pleasure tonight to introduce to you that team. And we really are spanning a large portion of the world. So I thought I would start from Europe and make our introductions, then going westward out to San Diego, where our presenter is. So to start off, what I would like to say is tonight's program is made possible by our National Science Foundation. And this is very important. They've supported us in this. And we have been preparing this program essentially since the spring. There's a lot that goes into this. So our means of bringing this to you as well to visualize these simulations is data visualization. And so I'm pleased to be wearing this shirt with our logo for Open Space. This is our freely available open source interactive data visualization software, thanks to NASA's support and the collaborative efforts with Linköping University in Sweden, also the University of Utah's Scientific Computing and Imaging Institute, New York University's Tandon School of Engineering. And Open Space has been built by students from the beginning. We also have our hardcore professional developers, but the way Open Space has been developed is really to have students with their master's thesis projects. And I'd like to introduce, without further ado, our two students who made tonight's visualization or make this science visible. And this is Emily Hu and Christian Adamson from Linköping University in Sweden. So Christian, wonderful, and Emily, wonderful.
Hi.
Great.
Hello from Sweden.
Yes. And so they've been diligently pushing Open Space into new territory. You can download Open Space freely if you're interested. Part of our team is in the chat. You will not see the content that we have just yet in the current release because our developers have to take what the students have done and put that into the main code. So working our way eastward, I'd like to introduce from NASA's Goddard Space Flight Center, Dr. Layla Mays, who is a solar astrophysicist and project manager for what we've been pulling together on this program. So Layla.
Hi, Carter. I'm excited for tonight's program.
Wonderful. And Layla and the students and the others I'm about to introduce will be in the chat if you're interested to ask questions during this. Also, very importantly, our pilot tonight for Open Space is Elon Olson. Elon.
Hi, everyone.
Elon has the task of actually driving us tonight. He is working for NASA's Goddard Space Flight Center now, working with Layla to basically bring the student work into the space of the code. And so he is working now with NASA Goddard. So now I'd like to bring us down to our collaborators at Johnson Space Center. This is where Mission Control is. And so Doctors Katie Whitman, who studies the sun, the solar weather, and highly energetic particles. Katie?
I'm from Houston.
Great. And also Dr. Phil Quinn, who also studies the solar weather, but advises Mission Control. Phil, great, wonderful. And last but not least, going farther west out to San Diego, so it's only about 3 in the afternoon there, is our presenter. And this is Dr. John Linker, who is the president of Predictive Science, Inc. And so John is going to take us through this. John.
Hi, Carter. I'm excited about tonight's presentation.
Great. We're going to start off with a quick introduction that Elon will be flying. So we're going to now transition into Open Space. Thanks. We're going to start here at the International Space Station. And I'm going to ask Elon if we could swing around, please, so that we can look down at the Earth from this. We're sort of looking up from the Earth at the International Space Station. Of course, this is this tremendous spacecraft that's been built over the past 20 years. What's swinging close to us are the Russian components, but really there are 11 countries. The first two pieces were launched from Russia, and then most of the space station being brought up in a multitude of space shuttle flights. And this is where humanity has been, essentially. It's been our destination in space. And so Elon, what I'd like to do is if we could pull back, please. And as we do, we can see the solar panels on the ISS. All together, that, with the solar panels, it's about the size of a football pitch or about a football field in size. And we're over Africa right now, and we're going to pull back. We see a trail now of the International Space Station. And what I'd like to do as Elon pulls out is I want to look toward the horizon. We can see our paper-thin atmosphere. It's only about 20 miles thick. And that's very thin compared to the 8,000 mile, roughly 8,000 mile diameter Earth. And interestingly enough, the period that it takes the International Space Station to go around the Earth is only 90 minutes. And we're looking at the day side of Earth here over Africa. And you can see that the orbit extends just slightly above the Earth, about 250 miles. What we'd like to do now is pull out even farther to give you a sense of satellites that we use that are vital to our telecommunications. And we're going to turn on the geosynchronous satellites, which sit out an orbit far enough, about 22,000 miles, to orbit the Earth in 24 hours. And that's why these satellites tend to hover over the real estate where they've been placed. And then a little farther beyond this, we're going to illustrate our Earth's magnetosphere. And this is from a simulation, and we see the field lines here in open space and how they bunch in at the North and South Pole. We call this a dipole. You may remember playing with iron filings on a piece of paper and a bar magnet. And so that is a North and South pole, and we call it North and South. Earth is fairly stable in its magnetosphere. We can see that it's sort of trailed off on the night side of Earth, away from the sun, and sort of pinched in perhaps on the sunward side. Also, this is generated by the Earth's outer liquid core. It's fairly stable. The polarity shifts or flips every about 100,000 years on a geologic time scale. But then also, how far away is the moon? And this is of great importance as we're just poised on the edge of going back to the moon. Of course, we had been there about 50 years ago. So Elon, if we could turn on the moon's orbit, please. It's about 10 times the distance of the geosynchronous orbit, or about 1,000 times the altitude of the International Space Station. We're going to be showing this trail. So the orbit of the moon is illustrated as a trail, and the moon is at the head of the trail there, just about to go into the magnetotail. The moon is 240,000 miles away. And I'm going to ask Elon to swing us around. We see a blue line. We see some other lines. These are the orbits of the planets. We'll see in just a second. But you may have noticed, if you've seen a total solar eclipse, that the moon covers the sun. They're the same size as seen from the Earth. This is an interesting sort of fact, but then the sun is much farther away than the moon. It's in fact about 400 times farther away. The moon is 1/4 the size of Earth, so if the sun is 400 times the distance of the moon, we'll start pulling away now from the Earth-Moon system, if we could, please, Elon. If we sort of go high inclination above, we'll also see the layout of the other planets. But the sun is 400 times the size of the moon, or about just over 100 times, 109 times the size of the Earth. Being the largest thing in the solar system, of course, we all orbit it. And so interior to the Earth, we see the orbit of Venus and then the orbit of Mercury. Mercury goes around the sun in 88 days. And then finally, we see the orbit of Mars outside the Earth, and that goes around in just about 2 years. We are passing Mars at the moment, but you may have noticed that there's a time counter in the upper left. we've set our sights for a particular event that was incredibly well studied in 2000 during the sun's solar maximum cycle. And so that will be our subject tonight. One of the last things I'd like to mention is the distance of the sun. It's about 93 million miles, or 400 times, or about, as I said, 400 times the distance to the moon. But there's also tonight, which is of special importance, is the speed of light. And so I'm going to ask Elon to turn on our indicator. And also, so it takes light 8 minutes to get from the sun to the earth. Now here we see this beam taking about 2 seconds. You may note in the upper left that we're doing a time lapse of 4 minutes per second. And so, but this will be incredibly important to look at how fast radiation from solar events gets to the earth. At this point, I think we should center on the sun, and I'm going to turn it over to Dr. John Linker, our presenter tonight, and we've been looking forward to this event. So thank you very much, John.
Well, thank you, Carter. Elon, please bring up the movies of the photosphere. And before we get started, I just want to take a moment to thank our sponsors again, not only the National Science Foundation, who Carter mentioned, but the science results we have today were also supported by NASA and the Air Force Office of Scientific Research. And the work I have the privilege of presenting to you today is really the work of several people at our company, Predictive Science, and also scientists at the University of New Hampshire. So what you're looking at right now then is a short movie of the sun's visible surface that we call the photosphere. This is actually what you can see when you look up in the sky with a telescope. Of course, you should never look directly at the sun. You should always use a projection or a filter that's guaranteed to be safe. But when you look at the sun's visible surface at solar maximum, which this is actually, this little movie is from July 2000, which was a period of solar maximum, you notice that you see a number of these blemishes we call the sunspots, these dark regions on the sun. And there's a solar cycle for these that takes about approximately 11 years. So we have, right now in 2020, we're kind of near the minimum of the cycle. We're just coming out of the minimum. We'll be going towards maximum. And so, there's 11 years from peak to peak. So it's really in about 4 or 5 years, we expect to be back at a maximum. We were, now these sunspots are important because they're the site of strong magnetic fields. In fact, that's why they're dark. They inhibit convection below the surface there. And so that part of the sun is cooler, and that's why it appears darker. And so, as I said, so magnetic fields are really the thing that makes the sun an active star. And these regions have strong magnetic fields, as I said. You can store a lot of energy there, and so that they are the source of these solar storms. I should mention that this photosphere that you're looking at is about 5,700 Kelvin. So now we're going to go up into the higher up into the solar atmosphere. And so Elon, if we can look now at the SOHO movie, I should mention that those images of the photosphere were also from this SOHO spacecraft, which is a collaboration between NASA and the European Space Agency. What we're looking at here on the left is you're seeing a extreme ultraviolet image of the sun from what is called EIT, or the Extreme Ultraviolet Imaging Telescope. And what you see there is, you see how there are all of these bright regions where you see like flickering and the sun's loops kind of appearing and disappearing. And these are called active regions, and they're basically associated with those sunspots. These active regions have strong magnetic fields there. And so because the fields are stronger, they're heated, the sun is heated more. That's why these are brighter. And the plasma density is also higher. And this is a good time for me to mention that up in the corona, the sun is what we call in a plasma state. So it's like a gas, but it's hot enough that the protons and electrons have been separated into this soup. So it's really a gas of charged particles. On the right-hand image, what you'll see is, first of all, there's kind of a black disk at the center, and the same image that we have on the left is superimposed over the center. That black disk is called an occulting disk, and this whole image is from the LASCO coronagraph aboard SOHO. And so a coronagraph makes what is like an artificial eclipse. This occulting disk blocks out the light of the photosphere so that you can see these white streamers above it. So if I think they're fairly apparent to you. And so you also notice, though, that in the midst of these streamers, you see big puffs going out and leaving the sun. These are called coronal mass ejections. They're often associated with some of the flickering and brightenings that you're seeing in the left-hand image, which are from solar flares. And flares and mass ejections are often, but not always, associated. These coronal mass ejections in particular are a major source of what we call space weather, though. That's the perturbations and other things that happen to the space environment. We're, of course, usually most concerned about that near Earth. And so what you see here then is that at this time of solar maximum, though, there's over this 2-day period, you're seeing a number of these coronal mass ejections, and that's that's just the way solar maximum is that there's plenty of activity. In the time period that we are in now, in 2020, there's a lot less activity. So now let's turn to the day of the event that we're going to talk about a lot today. This was on July 14th, 2000. This is the so-called Bastille Day event. And what you can see here is, in both frames, is that as you go forward in time, what happens is there's a strong, it's already happened, we have to wait for the video to start again. And what you see is in the left image, there's a strong brightening where there's a flash kind of across the screen. That was a major solar flare. It's what we call an X-class flare. Right associated with that, then it's somewhat hard to see, but in the right-hand image in the coronagraph, then shortly after that, there was a big coronal mass ejection that was aimed almost directly at Earth. And in that case, the white light forms a halo around the sun. You can imagine that if you have something that's coming right at you like this, then you just sort of see the outline of it. And so this was indeed this event. And the other thing that you notice is after the event happens, there's lots of static all in both images. In fact, the coronagraph frame actually totally kind of gets blipped out at one point. And so this is caused by solar energetic particles, chiefly protons. And that's going to be the focus of a lot of what we're going to talk about tonight. In particular, as we think about sending astronauts back to the moon, which in present plans will happen in the middle part of this decade, these highly energetic protons can pose a serious risk. And so we want to be able to, a lot of our work here is to try to understand and eventually predict these events, or at least give bounds on how serious they might be. So with that, let's go back to OpenSpace. And let's zoom in now. And let's turn off the background glow of the sun. And first, so now we're entering the world of our simulation. And our simulation is an attempt that we make to put as much physics as we know in and make a model that we can then look at and study as if it were the real sun. In this case, we're solving, this part of the model solves what we call magnetohydrodynamic equations that treat the sun as a magnetized fluid. What you're seeing here right now, the sort of bluish white are actually, that's showing you the plasma density in the simulation, and it's higher in certain regions. And Elon, if we could turn on the magnetic field lines now, you're going to see that this is associated, these higher density regions are associated kind of with magnetic field lines that are closed or stretch out, but they tend to start at one part of the sun and then come back. you see surrounding that, of course, is lots of open field lines. These are the field lines that stretch out into interplanetary space, and that's where the solar wind is free to stream outward. So when Carter was showing you the Earth's magnetosphere, you saw it had a kind of a much simpler structure. It had this kind of, basically a kind of dipolar structure. The sun also has the magnetic field, but it's much more complex. In part, that's because the currents that create that magnetic field are being driven by the plasma in the sun's interior. It's much closer, the generation is much closer to the sun's surface. And while there is generally like a single dipolar component of this magnetic field, you can also think of it as like the sun has lots of other little dipole moments all scattered around, and they make lots of different fields of larger scales and smaller scales. Finally, the thing to note is you'll see there's a green kind of map on the surface of the sun. That's actually then our simulation of what the extreme ultraviolet telescope that you saw, I showed you images from previously, that's what our simulation of that would show mapped onto the surface of the sun. And we'll be looking at some movies of that soon. But before we do that, let's put on our magnetic field map onto the surface of the sun. And let's take the density off. And so, as I said, solar activity is really all about the magnetic field of the sun. And what you're looking at here then is a map of the sun's magnetic field taken from observations during this July 2000 time period. And you see that there are red regions. This indicates where the solar magnetic field is pointed outward, and there are blue regions where the solar magnetic field is pointed inward. You'll also see that there's one region where there's a lot of detail of this. So you see lots of little pluses and minuses and things here. And the rest of the sun, it's much more smooth. And that's a computational choice that we make. We decide that we're going to put all of the resolution and that we have of the simulation concentrated in this region where this region actually occurred in the active region. And we still retain the structure of the sun's magnetic field in the outer part, but we smooth that out a lot. And as I said, that's really just to make the computation less expensive. One thing is let's maybe look down on this a little bit more, Elon, and then what I think you can see is there's kind of some snake-like field lines. And actually, let's rotate so we're more head-on looking down. Let's rotate, yeah, so that we can, and what you see there then is you notice that there's kind of where the red and the blue comes together. The boundary of that is what we would call a polarity inversion line. It's just basically because the magnetic field is changing sign, going from outward to inward. And along that, you see we have these snake-like field lines. And some of these are well, some of these are highly sheared that just go along. Some actually coil around other field lines. This is what makes what we call a flux rope. This is a highly energized configuration, like what the sun has before major eruptions. And in fact, it is along these polarity inversion lines that invariably happens, where you get this highly energized configuration. So let's now go back to our simulated EUV texture on the sun. Yes, so now we're looking at our simulation of what the extreme ultraviolet, this would be the 195 angstroms, if you're, which is generally plasma that's on average is about 1.5 million Kelvin. I should have mentioned that the corona is much hotter than the photosphere. And what you see is that this is much brighter in the region where we have our flux rope and our active region. That's because the fields are a lot stronger. The plasma is heated a lot more, so it's a lot brighter, and it's also a lot denser. So now that we've done that, let's try to go forward in time here and start looking at a movie of our actual eruption. So the way we start this out is we start out by making a stable structure so that if we don't do anything else, this will sit in equilibrium or evolve slowly. We then, in this case, we move the fluxes around on the photosphere a bit, as actually happens on the real sun. We just do a kind of idealization of that. This perturbation causes the system to be unstable, and now you see that this magnetic flux row erupts outward. And I think you can also see, as it erupts outward, that you get these large brightenings that are in our extreme ultraviolet right there on the surface. And this is all strongly related to a process called magnetic reconnection, where magnetic field lines can come together and reconfigure. And that process can release a lot of magnetic energy. And in our simulation, it is the primary mechanism by which the magnetic energy release is occurring. One of the reasons why we do this simulated extreme ultraviolet is, of course, it gives us an opportunity to compare with the actual observations. So Elon, if we could actually now go to our movie of the simulated EIT comparison. So on the right is actually the same EUV extreme ultraviolet movie that you saw earlier. And you again see that there's this bright flash. And I should mention that that's not what's really happening on the sun, in the sense that's not, the ultraviolet isn't actually streaking out that way. This is an effect that, because the emission is so strong, there's so many photons, it overwhelms the detector and it bleeds into the, and so there's bleed into the other elements of the detector, and that's why you get this streaking across. On the left now, you see our simulation of this same event. And the first thing you notice is that our simulated sun is a lot simpler than the real sun. And that's, as I said, that was a computational choice. We put most of the resolution of this simulation right around this region where the eruption actually occurs. And then we smoothed out the magnetic fields of the rest of the sun. The large-scale magnetic flux is actually not very different, but now these other active regions are not really present in our simulation. So we see, in fact, then that this is one of the indications that our eruption is sun-like, if you would like, even though it's not exactly like the sun. We can now zoom in with a second movie taken by the TRACE spacecraft. This was another spacecraft that was up at this time that also looked at the sun in extreme ultraviolet, but focused on just portions of the sun at much higher resolution. And so what you're seeing on the right is again from our event here. You see like this glowing worm-like structure forms, and that's actually, as you saw in our simulation, that's actually occurring in the aftermath of this flux row propagating out. It's part of this reconnection that forms new loops that are closed, that are very hot, and also very dense. This structure has often been called the slinky. If you look in the left now, in our simulation of this event, you can see that we get some things that are very similar. We again get this kind of deep brightening and some propagation going kind of from left to right. You can kind of see though that for much of this though, we sort of have a lot more emission surrounding us in the simulated thing, whereas it's almost completely dark. And that's really because we don't get as intense change in the brightness. These are both scaled, these are continually scaled to the maximum brightness. And so whereas in the TRACE movie, if you go back and look at the EIT, you'll see that there was actually lots of emission there. It's just that this emission is so much brighter, it's overwhelming everything else. Well, let's now go back to open space. And so now, and let's start looking at our simulation here with the light on. So now what you see as we look from a little bit farther away, you see that our coronal mass ejection, our simulated coronal mass ejection, leads to this kind of explosion of magnetic fields going out into the corona. And all of those magnetic fields that were originally this kind of relatively simple flux rope plus other surrounding fields have now bundled into this huge thing that's propagating out. These field lines all pretty much still connect back to the sun. You also see associated with it now this large clump of density that we're showing as this kind of ghostly cloudy blue. And so that in fact is how coronal mass ejections get their name. There are regions of much higher density, but in terms of space weather effects, it's often really the magnetic field going out with them that is responsible, for example, if it interacts with the Earth to cause geomagnetic activity. So now as we swing, this is good, we swing so we're looking kind of head on at our coronal mass ejection. You see this thing puffing out at us. If we just stop right there for a moment, that's really good. So this is almost exactly what the Earth view would be of this. And so again, we can use our simulation to create images like would have been observed if our simulation was the real sun. So Elon, if we can go to our movie of the coronagraph. So now on the right, this is another coronagraph image from SOHO. This is now what's called the outer coronagraph. And I should have mentioned before that the little white circle in both cases is actually the position of the sun. That's the radius of the sun. Now we have you see there's another kind of blackish disk here that is the occulting disk. So in this coronagraph, I should say in this outer coronagraph, it allows you to see much farther out, but blocks more of the light on the in part of the sun. And what you see is that you see this big halo. First, of course, you see the streamers. Then as the eruption starts, you see this big halo, and then it's completely overwhelmed by the static. These are these solar energetic particles that we are so concerned about. On the left, you see our simulation of this event has a very similar aspect. Of course, because it's a simulation, we don't have to worry about energetic particles hitting our computer. What you see is, in particular, we get this kind of large halo going out, and the speed of the measured speed of this CME close to the sun was about 1,700 kilometers per second, and our simulated CME had a very similar speed. It was actually a little bit faster low in the corona. Let's go back now to open space. So now as we look at our CME propagating outward, this would be a good time for us to, so as I mentioned, this CME is going about 1,700 kilometers per second. That's about 4 million miles an hour. That's very fast. But now we're going to start talking about our solar energetic particles. So Elon, if you could turn on the nodes visualizations now. So the second part of how our simulations work is in conjunction with our magnetized fluid that we model. What we do is we place what we call nodes into the flow of our simulation, and those all propagate out into the solar wind and interplanetary space. And along these nodes, we calculate distributions of how protons will behave under the forces from this magnetized fluid. And so when we do that, I mean, the simulation, this is called the solutions of the focus transport equation. You can think then that each of these nodes, we are calculating proton intensities. And if you could now, yes, excellent. You can see on the right there is a palette that shows you how intense these are. And what we're focusing on here are greater than 100 MeV protons. These are very high energies and are definitely of concern, the most concern for astronauts. And you can see then that how these are propagating out rapidly. Elon, if let's see, can we get our, get our speed of light indicator on here. So this again goes back to one of the most dangerous aspects of this is that these particles arrive very rapidly. When you're looking at the sun and, for example, you see that flare, that image is 8 minutes old. It's taken 8 minutes to get to you. These highly energetic protons, they're not as fast as light, but they can be very close. So within about a half hour, you start getting high intensity particles reaching you. So this does not give us a lot of warning for astronauts. Now, if we could start to zoom out a little bit more. We see more and more of you can see these particles, how they go far out into interplanetary space. And yes, there's our light indicator. So now we're going out farther. So you start to see the orbits of the planets and how these energetic particles that we're visualizing on these nodes. You can think of these nodes really as detectors in our simulation. How they are spreading outward. And you notice how they may get this spiral effect. That's because the sun rotates. And so as the sun rotates, it's kind of like having a sprinkler that rotates. It sends out a spiral pattern of the water. In this case, because the magnetic field is tied back at the sun, as it goes outward and rotates, it forms a spiral pattern. And in our case, the magnetic field really channels these solar energetic particles. So in some sense, we're actually visualizing the magnetic field by just looking at the streams of nodes that have followed kind of the path of the solar wind. And so the other thing you'll notice is that this is clearly filling up a vast part of the solar system. In fact, we actually have nodes everywhere, even places where you don't see particle fluxes, but where those fluxes are low, we're just not plotting them. So you see this spiral pattern. Again, with our speed of light indicator, though, you can see that here we're looking at the orbits there. The little white at the end of the blue, that's actually our Earth-Moon system. You can see how then our particles are how these energetic protons are making it out very rapidly to the Earth. Also, because they're going across a vast part of the solar system, if you're thinking about interplanetary travel to, let's say, Mars with astronauts, you also have to be very concerned about these events, because it's clear that one event can spread a lot of radiation throughout the solar system. So to get a little bit better view now of these, let's turn on our our sun's equatorial plane. So what we're doing now here is projecting the proton intensities into this heliographic plane. That's really essentially the sun's equatorial plane. And that plane is very close to the plane of the orbits of the planets. And so this gives you kind of a very good picture then of how the intensity is spreading out. In looking at this, you can see that the Earth, while it's in a very intense part of the radiation storm, it's actually not in the most intense part. This is of course based on our simulation. We only have measurements from the Earth for this. In our simulation, we're finding that in fact the event would be even more intense if you were sort of to the left of the Earth, what we would say if you're standing on the Earth, you would call eastward. And that is actually a well-known effect that generally because the particles propagate along this spiral. This is, by the way, known as the Parker spiral, because it was Eugene Parker who proposed and was correct about the solar wind. So now to get more of a three-dimensional view Let's turn off the heliographic plane and let's look at our, what we'd call a meridional plane. So this is just a plane that's just perpendicular to the other plane, and we're projecting now what the proton intensities would be in this plane. And you can again see that this is spreading out widely. So this is a fully three-dimensional structure of proton intensities. And you can see that it actually gets to fairly high latitudes. Now, if we turn our heliographic plane back on, this then gives you this kind of three-dimensional view, or more of a three-dimensional view of this. You also just see how vast our solar system is compared to the Earth-Moon system, which, as I said, is just a little white dot over there that you see the speed of light keep propagating towards our little dotted indicator there. So now, I think this is probably a good time for us to go back to our node visualizations. So now, as we see our node visualizations here, you can see how, and let's start to zoom in more towards the Earth. But first, again, you get this sense of how big the solar system is compared to us. So, here on our tiny Earth, or even just the whole Earth-Moon system. And that as you come in here, you can see that, again, you're struck by, or I am always, that this is not much slower than the speed of light, and so how rapidly these things can get to us. And this is one of the issues for forecasting. You also see that there's a fair amount of variation, although the proton intensities are kind of high in most places, there's a fair amount of variation here. And also that even in our simulation where we have over 1 million of these nodes, that we're still kind of sparse right around the Earth here. But what we see then is there could be a lot of variation. And this is one of the things we want to look at in terms of forecasting or warnings, is trying to have a range of uncertainty of how strong the fluxes could or might not, or could not be. If we now, let's turn on, now what we've done is we've brightened the nodes that are closest to Earth, so you can really see their, you can really see the intensities right there. And so I think this would be a good time to actually, let's start to really zoom in and turn the Earth's magnetosphere back on. If it's, so now we think about our Earth-Moon system and how we have these solar energetic particles that, chiefly protons, that can propagate rapidly here. And now we're talking about having people go to the Earth-Moon system, or in particular go to the moon. And so this poses radiation risks. How can we possibly mitigate these risks? First of all, one of the concerns is what are called EVAs, or extravehicular activities. So when such an event is going on, you do not want the astronauts to be outside of their spacecraft or their shelter on the moon. You want them to be inside, because the walls of the spacecraft do provide some protection, but they don't provide complete protection, because these are very energetic particles. They can penetrate the walls of the spacecraft. They can also, when they hit the walls or interact with the walls of the spacecraft, create secondary radiation. And so NASA has mitigation plans for this. And so if we could switch to our movie of the crew in the cargo bay of the Orion spacecraft. So this is a practice that astronauts are doing of how they could shelter. And so the main thing that you want to do is have as much material around you. And for example, in the space station now, they have regions that are more shielded where they will go if an event is ongoing. The space station, though, is deep within the Earth's magnetosphere and has a lot more protection than a spacecraft that's outside of it. And so what they're doing here then is they're kind of burrowing into the cargo bay, piling all this stuff around them, And that actually then gives them extra protection because although you won't, if they're inside the spacecraft, you're not likely to have an acute event where they get radiation poisoning right then and there. You're also worried about their long-term cancer risk. And in particular, after they've been exposed to a certain level of radiation, they may not be able to be crew anymore. And so, so all of this is to reduce that radiation exposure as much as feasible. The other thing you notice about this is that this looks like, this time-lapse photography, this looks like a lot of work. And so it takes them about a half hour to do this. And so you definitely don't, while you want to be able to give them warning and accurate warning, you can't give them false warnings because no one's going to want to go through doing this unless they really need to. Let's go back then to OpenSpace here and talk about a couple of other aspects of this. First of all is that it was, that of course this risk has always been there. In fact, in August of 1972, there was a very large solar event, very large radiation storm that occurred between two Apollo missions. One was in April and one was in December. And back then NASA did know about risks of solar energetic particles, but we didn't know nearly as much about the sun. We didn't have nearly as good observations. For example, they did look at sunspots and knew that could be dangerous. Now, because we have many more observations that are ongoing at what we often call this heliophysics observatory, it gives us more opportunity to, and also we have NOAA GOES satellites that are geosynchronous, that in fact where we often measure these protons. They give us more, gives us more opportunity, first of all, to understand these events better and to give warning. Last thing I'd like to note, of course, is that I've really talked about one of the risks of radiation for astronauts. This is this kind of acute risk that you're really worried about. For example, you don't want astronauts walking around on the moon when an event like this is happening. So, but there's another risk that comes from energetic particles from outside our solar system. These are so-called galactic cosmic rays, or GCRs. These have much lower intensities. There are much fewer of them, but they're much, much higher energies, and that makes them much harder to shield against. So now when you're thinking about, and they're always there. So on a longer crewed mission, for example, when you're going to Mars, you really have to worry about how we can mitigate the possible radiation from GCRs. In fact, it takes you to almost thinking of, well, here you may be thinking you're worried most about solar maximum. GCRs are strongest in solar minimum. And so in some ways, you might actually want to travel at maximum to avoid the GCRs, but and deal with the solar energetic particles from which we can at least make some predictions and look and have better plans for mitigation. So with that, I'll close and ask for questions.
Awesome. Thank you so much, John. That was a really great presentation. I'll add you as a spotlight with me. Give you a round of applause. Feel free to use your reactions, everyone in the audience. So we have actually a lot of great questions.
Yeah, okay, so I see. So this is different than maybe like one of the kinds of radiations people think about is like when you have radioactive elements on the Earth, okay, like plutonium or something, it's decaying, giving off radiation. This is different in the sense, for example, that might be neutrons, or even, you know, gamma rays. But in this case, this is actually, these particles are being accelerated at the sun or near the sun as this coronal mass ejection propagates outward, and then they propagate out towards you. Now, as you go farther out, they are generally going to expand, and so the fluxes of them are going to be lower. The intensities are going to go down, but the particles themselves don't really lose energy. I would say, well, first of all, we had much less, our knowledge of solar energetic particles was less than, but we knew about them. They knew this was a risk. They really didn't have any mitigation strategies other than you know, I suppose that they could have decided not to get out of the lunar module or something if they thought. But you know, we didn't actually have the same kind of monitors in space to know that the event was going off. This event that happened in August 1972 was mostly seen as like it was an absolutely huge flare. If you go Google, you can find Seahorse flare. There's a picture of it in H alpha. Many interesting aspects to this event that scientist Dolores Knipp wrote, I think it's a space weather article about. One of the things that happened was the geomagnetic activity was so strong, it set off mines in Haiphong Harbor in North Vietnam. Okay, well, I have heard of this TV show, but I haven't actually seen it, I have to say. So what I would say is that in general, one of the things that we worry about for extreme coronal mass ejections is they could indeed affect our power grid, because you can get geomagnetic storms. These storms can cause ground current, basically, and the currents aren't really that large, but particularly they're direct currents. And so we know, for example, in a major storm in 1989, the transformers in a power station in Quebec were damaged. They went down, they lost, and a portion of Quebec lost power for a significant, for a significant amount of time. And so I think the problem is that indeed there are, I'm not a power engineer, there are mitigating steps that they can take though, to try to, and in particular with a grid, when you have a power grid, we're going to want to think about how to limit the propagation of things. But power grids are very complicated, and we've already had events in power grids that are not space weather related that we don't fully understand. I know there was one in San Diego 8 years ago where somebody cut through a line and all the power south of Orange County went out. And even though they were supposed to have all these backups, that cutting through that line wasn't supposed to make that happen. It did, okay? And so I think where space weather really stresses our system then is that power grids are really complex. So just saying, okay, let's just cut all of our lines and everything, it's not easy. It's a drastic step. And also, that's right now our predictability isn't good enough. That is, we can tell you, oh, there could be a really large event, and but sometimes a good example is in October 2014, the largest sunspot in 25 years came up and rotated across the disk. And for example, like it was a sunspot nearly as big as in 1989 where Quebec lost power and the northeast of the US nearly lost power. But now we have this huge sunspot, and although we had some very large solar flares, it turned out there were no important coronal mass ejections, and there was very little space weather effects. So part of that is on us as scientists to get a lot better at this.
Awesome, thank you. So our next question actually comes from a 5-year-old audience member, and it's a little off topic, but I thought it was a really good question. So John, if you can't answer it, we can definitely throw it out to our larger panel of experts here.
The Milky Way, so our sun is a star. It's the closest star to us. In fact, we're in a solar system with planets around it. In fact, we're in a galaxy, what's called a galaxy, which is lots and lots of these solar systems, okay? And there's lots and lots of stars. And so when you live in an area that doesn't have too much light pollution, you can look up at the sky at night on a dark night if it's not cloudy, and you can kind of see the background of lots of these stars. I don't know if someone has, maybe Carter would like to jump in with further comment on that, but.
I'll just mention that there are so many stars in the Milky Way galaxy that we estimate from very good estimates, but in excess of like 200 billion stars. And we've measured distances just recently with a new mission called Gaia to 1 billion of them. So less than 1%, but still that's a lot of stars. And it all comes together with gravity, kind of the same way that the planets came together and the stars come together. So if you are interested, just as you go forward, take up physics and start to understand the process of nature and how that all works.
Well, those are great questions, actually. So I would say that it's not necessarily the case. If you're thinking of the white light movies that we were showing from SOHO, it's not necessarily the case that they're always going off on one side or the other. But when you're looking at the sun with a coronagraph like that, and you have and so you're putting this occulting disk, and so it's blocking this light of the sun. It's easiest to see coronal mass ejections that are going off kind of on either end. The ones that are coming towards you like that, like the big one that we talked about, you only see as a halo, and generally it has to be a really fast, strong CME to get that halo. The second question about mass loss from the sun is that I would say that it's not. I don't think that really contributes to the lifetime of the sun. I think in the sense of that what kind of mainly it's the hydrogen burning in the sun that kind of determines its lifetime. There's a certain point where it starts to burn through other stuff. It gets too hot, and then and a star like the sun will then expand outward and become a red giant. But mass loss in stars from winds and from activity like coronal mass ejections is something that is of interest to understanding, especially I think in many more active stars or younger stars where the winds can be a lot stronger.
Awesome. Well, thank you so much for John for delivering such an amazing presentation, to all of our collaborators for making the simulations possible. It's been lovely to have you all with us for our first ever Virtual Frontiers.